SAS demonstration, Statistical Test 1. For this demonstration, I'm using a data set called Pulse. And this data set consists of 92 subjects. 35 of the subjects were asked to run, and 57 of the subjects were not asked to run. Subjects had their pulse rate recorded before the activity of running, and then they had a second pulse rate recorded for those subjects who ran after they ran, and for those other subjects who did not run, a second pulse rate was recorded. Subjects were also classified as to whether they normally engage in low, medium, or high activity. So the data set that I'm bringing in is a CSV data set, which is a type of data file that you can produce from Excel. And normally when you produce a CSV file, you're going to want to read in the data from the second row, because the first row of data is usually the column headings from the Excel spreadsheet. And a CSV file is a comma delimited file, and so we have here the option delimiter equals comma, or you could have said DLM equals comma. And then I also have the misover option included because I know there are some records that are shorter than other records. And so I'm inputting the following variables: pulse 1, which is our resting pulse; pulse 2, which is the second pulse rate; whether or not the subject ran; the subject's smoking status; their gender; height, weight, and normal activity level. And you see here that I have a Proc format where I've created formats for gender, I've created a yes-no format, and an activity format. And then within my data step, I'm creating a variable called pulse diff, where I'm subtracting the resting pulse from the second pulse that was recorded. And I'm calling this data set Pulse, so it's a temporary SAS data set. So the first thing I'm going to do is I'm going to do a contents of my data set, and then I'm going to print out the first 25 cases. And notice that I have my format statement within the data step, and so that in all the subsequent procedures you will see formats attached to the variable codings. So here is the results of our proc contents procedure. We see here we have 92 observations and 9 variables. These are the variables in our data set. We see the formats that were attached, and we see the labels that were attached. And then here are the first 25 observations. So we see all 9 variables plus the new variable we created in our data step called pulse diff. The first kind of test that I want to show you is a one-sample test for proportion, which is also referred to as the binomial test. And the way we do this is we're going to use Proc Freak, and all we have to list is the one variable, smoke, because what we're interested in testing is whether the true proportion of smokers is equal to 0.25. So in our group of subjects, is the true proportion of smokers 0.25? And so here, to do that test, we have a slash after the variable smokes. We're listing our test, which is binomial, and we're indicating what the proportion is that we want to test. So this is a one sample test that we are conducting here. So here is the output for our one sample test, testing that the true proportion of smokers is 0.25. One of the nice things about this option binomial is it also gives us the 95% confidence interval for our proportion. And it calculates the 95% confidence interval for the group that's listed first. So here, since our formatting order was 1 equals yes and 2 equals no, our 95% confidence interval is around the proportion of smokers in our data set. So we see here that about 30% of our study group were smokers. The 95% confidence interval goes from 0.21 or 21% to about 40%. And then here is the results of our test for whether the proportion of smokers is equal to 0.25, and we see that we have a non-significant result our p equals about 0.23, so we cannot reject our null hypothesis that the true proportion is equal to 0.25. Another kind of test you can do where we're only looking at one category is the chi-square goodness of fit test. And to do a goodness of fit test, again, we're just looking at one category, activity. All we need is the chi-square option. And what we are testing is whether the proportions in each category are equal. So based on our study group, do we have a similar proportion of subjects who are engaged in low, medium, and high activity? So let's see what the results look like here. So here we get our frequency for activity, and the chi-square test for equal proportions we see is very highly significant, less than 0.0001. So we are going to have to reject the null hypothesis that the proportion of subjects engaged in each level of activity is the same. Now let's say based on prior data we have some hypothesized proportions that we want to specify. Let's say based on some research we believe that only about 20% of a sample of subjects of this particular gender distribution and age distribution are going to be engaged in low activity. About half of the subjects we expect to be engaged in medium activity, and only about 30% are engaged in high activity. So we're actually specifying the proportions here. So let's take a look and see if our p-value changes based on these specified proportions, or whether we again have a highly significant p-value for this goodness of fit test. So here again, we now have our chi-square test for specified proportions. The p-value is not quite as significant as previously, where we were looking at equal proportions in each category, but it's still very significant with p-value of 0.0058. Notice here we are shown the test percentages that I had indicated for this goodness of fit test. So here we've been looking at one sample test with proportions or categorical data. Now let's look at the one sample test when we're dealing with continuous data. So to do a one sample t-test, we're going to use Proc Univariate. And here we're interested in doing a one sample t-test where our null hypothesis is that the pulse rate at time 1 is equal to 72. So to do a one sample test with the null hypothesis that the pulse rate is equal to 72, we have to specify mu0 equals 72. If we left this out, then we would just be testing whether the pulse rate is different from 0. I've also requested a histogram and a normal probability plot because we want to see if the distribution of the variable pulse at time 1 is normally distributed. Of course, in this situation, we do have a large sample size of 92, so by the central limit theorem, it would be okay if we did this one sample t-test, even if the variable pulse 1 was not normally distributed. But I thought to include the plot so we can assess whether it's normally distributed. So let's take a look at this output. Okay, so first of all, we're going to look at the output for Proc Univariate. So here we start, again, Proc Univariate generates a lot of output. So if we go from our moments and basic statistical measures down to our tests for location, here we see the test of whether our pulse is differing from a population value of 72. And so if we look at the student's t-test, this is a one sample test, we see that the p-value is 0.45. And so we cannot reject our null hypothesis and conclude that the pulse rate differs from 72. It does not appear to differ from 72. If we scroll down a little more, we also have the test for normality, the Shapiro-Wilk test, and we see here that the p-value is about 0.05. So based on the Shapiro-Wilk test, we can't necessarily conclude that the data is not normally distributed. And then if we go and look at our graphs, we see here that the resting pulse rate really does look kind of normally distributed here. And if we look at the QQ plot, we don't see any extreme departures from normality either. A second way that we can do a one-sample t-test is with Proc T-Test. And so basically, with Proc T-Test, we have our Proc T-Test. We're telling SAS what our null hypothesis is going to be. So we're interested in testing whether pulse rate is equal to 72. And all you need to list in your procedure is the variable pulse 1. And that will produce a one-sample t-test. So let's run this code. So this is another way of doing a one-sample t-test. And we see here that our results are exactly the same as what we got in Proc Univariate. We have a p equal to 0.45, and again we would conclude that we can't reject our null hypothesis. So there are two ways to do a one-sample t-test. So now we're going to move on to looking at two variables. So first of all, we're interested in looking at the association of two categorical variables. And we're interested in whether gender and smoking are associated. So to do that, because we have two categorical variables, we are going to use the chi-square test. And basically, after the table statement and the slash, we're just listing the option chi-square. So here we see our cross-tabulation table of gender and smoking. And if we scroll down, we see the results of our chi-square test. So there are a number of statistics that are shown here. I normally focus on the chi-square statistic, and we see that the p-value is about 0.22. Below it, SAS automatically prints out the Fisher's exact test for 2x2 tables. So here the Fisher's exact test is 0.25. So based on these p-values, it does not appear that there is an association between gender and smoking. Let's say we were interested in looking at whether there's an association between gender and activity level, and we want to suppress some of our percentages. So let's say we're not interested in the column percentage and we're not interested in the overall percentages. We're going to suppress them. And let's say we're interested in seeing the expected cell counts, because again the chi-square test is based on looking at expected and observed cell counts. So let's see what happens when we run this analysis. So here we have our 2x3 table, and notice we are shown our frequency, our expected counts, our row percentages, and that's all. And so our expected counts are based on our marginal distributions. Now let's say we were interested in doing this exact same test, but we want to focus on just non-smokers. So in order to just focus on non-smokers, we're going to have a where statement where smokes equals 2. And so we're looking at the association of gender and activity among non-smokers only. So let's look at that. So here, again, it's just for non-smokers. So now we're only dealing with 64 subjects. And when we do a table that's larger than a 2x2 table, we don't automatically get Fisher's exact test. We only get the chi-square test and some of these other statistics. But because we are dealing with smaller expected cell counts, we get a warning here. It says 33% of the cells have expected counts less than 5. Chi-square might not be a valid test. So if we go back and look at the table of our expected cell counts, we see that in our first cell of males who engaged in low activity, the expected count was about 3.5. For females engaged in low activity, the expected count was about 2.5. These are for non-smokers. And so SAS automatically gives us this warning. And when you see this kind of warning, you're not going to want to use the chi-square test. You're going to want to do the Fisher's exact test. So to get the Fisher's exact test for tables containing sparse cells, we just add the exact option here. Or you could actually write a separate statement, exact Fisher. And this is one of the nice things about SAS compared to SPSS, because in SPSS you only get Fisher's exact test for 2x2 tables. So here I'm rerunning this code with the requesting Fisher's exact test, and you see here that we have our results, and based on Fisher's exact test for non-smokers, there does not appear to be an association between gender and activity level. In this next bit of code, I'm interested in checking the normality assumption of the type 2 pulse rate by running status. So I'm going to show you a QQ plot as well as a box plot. So first of all, let's look at the QQ plots for pulse rate at time 2 by running status. And I'm particularly interested in the plots here. So we're going to go and look at the plots. So first of all, if we look at the histogram, it does not appear that the data is normally distributed for those subjects who ran and then had their pulse rate recorded at time 2. For those subjects who did not run and had their pulse rate recorded at time 2, it does appear that the data looks more normally distributed. And here is the QQ plot for subjects who did not run. So their time 2 pulse rate, again, the data appears to be normally distributed. For those subjects who did run, the QQ plot indicates that there's some departure from normality. So it's not surprising that those who did not run, their pulse rate at time 2 appears to be normally distributed, because when we looked at pulse rate at time 1, the baseline pulse rate, that appeared to be normally distributed as well. For those subjects who ran, their pulse rate, of course, is going to be affected by the intervention, and that may partly cause the difference in why the data does not appear to be normally distributed at time 2. Another way that we can compare the test variables visually between the two groups for both location and spread is with a box plot. So again, I'm interested in looking at both the baseline pulse and the time 2 pulse by whether or not you ran. So here's the box plot for the resting pulse rate, and it appears that just looking at it that there's not much of a difference in pulse rates between the subjects who were given the intervention of running and the subjects who were given the no intervention at all. So this was the resting pulse rate of everyone before the intervention of running. And then if we look at the second box plot, not surprisingly, those subjects who were asked to run, their pulse rate is much faster than those subjects who were not asked to run at all. And it also appears that the distribution of those subjects who were asked to run, the distribution of their second pulse rate does not appear to be normally distributed compared to the subjects who did not run and had their pulse rates recorded at time 2. So basically what I've been doing here is just kind of doing a little background work before I conduct my independent sample t-test. Again, one of the assumptions of the independent sample t-test is that each of our samples are normally distributed, unless the sample size is greater than 30 for each of the groups. Now we do have that situation where our sample size is greater than 30, so it's not of so much concern whether each of the groups are normally distributed. However, only 35 of our subjects were asked to run. It's a good thing to check the distribution of these continuous variables for each of our running groups because the groups are not that large. So here is the independent sample t-test. We have Proc T-Test, and when we're doing an independent sample test, we have a class statement, which is where we list our categorical 2-level variable, and then we can list as many variables as we want that we want compared between those two groups. So here we're interested in both comparing pulse 1 and comparing pulse 2 between the two groups. So this is our output from pulse 1, the variable resting pulse rate per minute. And first of all, Proc T-Test produces some simple statistics for the group that ran, for the group that didn't run, and then for the difference, 1 minus 2. So it gives us automatically the mean, the standard deviation, standard error, minimum and maximum. It also gives the 95% confidence limits The first thing that I look at from the output for the t-test procedure is whether we have equality of variances. So based on this p-value, I would conclude that yes, the variances appear to be equal because this p-value is not significant, and so that I'm going to look at the p-value under the pooled method where variances are equal, and this p-value is 0.62. So based on this p-value, I would conclude that the mean resting pulse rate is the same between those who ran and those who did not run. Now let's take a look at pulse rate 2. Again, we have our descriptive statistics, and if I go down and I look at the test for the equality of variances, I see that it's highly significant. So I'm going to conclude that our variances are unequal. And so then to get my t-statistic, I'm going to look under the method Satterthwaite, because it's the test where we have variances that are unequal, and you see it's very, very highly significant. So I'm going to conclude that the mean pulse rate taken at time 2 differs between those who ran and those who did not run. If you have a very large N for each of your groups, you don't normally have to worry about the equal variance issue. But I'm just showing you how I go about interpreting this output. Let's say I was concerned that the distribution was not normally distributed in each of the groups, and these group sizes are not that large. The other thing I could do is the Wilcoxon rank sum or Mann-Whitney test. Those names are interchangeable. It's the same test. And to do that, I'm going to use the procedure n-par one way. And I'm going to put in the option Wilcoxon. So this is going to give me a 2 independent group test using non-parametric methods. So basically we're going to be comparing the medians between the two groups, those who ran and those who didn't run. And you see here that the statements are the same. We have a class statement and we have a var statement. So let's see what the results are when we do a proc n-par one way. So this is what the output looks like from proc n-par one way. And I usually focus on the two-sided normal approximation. And it says here it's less than 0.0001. And this is for the pulse rate at time 2. So based on this result, I would conclude that at time 2, there is a significant difference in the median pulse rates between those who ran and those who didn't run. And scrolling up, if we look at pulse rate 1, here our p-value is 0.85. So based on this p-value, I am going to conclude that the median pulse rate at time 1 does not differ between the two groups. So again, the results of these non-parametric procedures is the same as the result we got using Proc T-Test. So now let's look at paired data. Let's say we were interested in testing whether overall the pulse rate at time 2 differed from the pulse rate at time 1. And so since each of these pulse rates were taken on the same person, we have paired data. And to do a paired sample t-test, we can do that by using the paired statement in Proc T-Test, and we have an asterisk between the two paired variables. So if we run this, we see that our probability is less than 0.0001, so there is a statistically significant difference in the pulse rate at time 2 compared to the pulse rate at time 1 if we include all 92 subjects together. Let's say we want to do a paired t-test for the group of subjects who ran and the group of subjects who didn't run. Then we are going to do our Proc T-Test by the variable ran, and let's see how the results differ here. So for those who ran, there was a very significant difference in their time 2 pulse rate compared to their time 1 pulse rate. For those who did not run, you see the p-value is 0.85, and so we would conclude that there is not a significant difference in the time 2 pulse rate compared to the baseline pulse rate for those subjects who did not run at all. Another way that you can do a paired t-test is by using proc means. And so here, in order to do it in proc means, we are using our variable pulse diff. And basically what we're testing is whether this difference in the two pulses differs from a value of 0. And so we're doing essentially a kind of one sample t-test here. And we're requesting the t-statistic and the probability value in our proc means statement. And we want it for whether or not you ran or did not run. And so we have class ran. So this is a second way of doing a paired t-test. And you see here we get the exact same p-values that we did before by using the variable that we created called pulse diff. And so for those who ran, there was a statistically significant difference in their pulse rates between time 1 and baseline. For those who did not run, there was no difference in their baseline and time 2 pulse rate. And finally, a third way that we can do a paired sample t-test is with Proc Univariate. And we again put the variable pulse diff into Proc Univariate. And if we look at the output, and we're interested in the tests for location, so we're testing here whether pulse diff differs from a population value of 0. So mu equals 0. And here we're looking at all 92 subjects together. So we're combining those who ran and those who did not run. There is a significant difference in pulse rate between baseline and time 2 for if we look at all 92 together. And the reason for this is because we have those subjects in there that ran as well as the subjects who did not run. What's also helpful with Proc Univariate is besides getting the student's t-test, we're also given the non-parametric test, the signed test, and the signed rank test. So if you were doing a paired test with continuous data and you were concerned about the normality assumption, then you would want to use the univariate procedure to do that. And so if you had a recording like pulse at time 1 and pulse at time 2, you would want to create a variable, the difference, which is what we did, pulse diff, and then run that new difference variable in Proc Univariate. And that would be the way that you could conduct the signed test or the signed rank test. So you need to use Proc Univariate for those two non-parametric tests which are used for paired data in the setting where the data is not normally distributed. Finally, I want to look at paired categorical data. So I'm going to create a new data set called new pulse. And so I'm going to bring in my data set pulse, and I'm going to categorize the pulse at baseline as whether or not you had a high pulse rate or a lower pulse rate. So if your pulse rate was greater than 80, I created a variable high pulse 1 equals 1. If it was between 0 and 80, then high pulse 1 equals 0. And then I did the same thing at time 2. And so if I want to see if the proportion of subjects whose pulse rate was less than or equal to 80 at time 1 differs from the proportion of subjects whose pulse rate was less than or equal to 80 at time 2, to do that, because this is paired categorical data, I would use the option agree, which gives me McNemar's test for paired categorical data. So first of all, I'm just printing out my new variables that I created. Here is my high pulse variable at baseline and my high pulse variable at time 2. And then to do McNemar's test, we're just going to do high pulse 1 asterisk high pulse 2 with this option agree. And we see here that McNemar's test, the p-value is 0.0076. So we are going to conclude that the true proportion of subjects whose pulse rate was less than or equal to 80 at time 1 differs from the true proportion of subjects whose pulse rate was less than or equal to 80 at time 2. And the agree option also provides us with a Kappa statistic. And so here our Kappa statistic has this value. It's kind of like a correlation coefficient. It has a value of about 0.57. So if we go back to the code, I've given you an interpretation of kappa values. So we see here that our kappa value falls within this range of 0.41 to 0.60. So we have moderate agreement between our pulse rate at time 1 and our pulse rate at time 2. So you can see that a lot of the procedures that we have been using throughout the semester, particularly Proc Freq and Proc Univariate, can be used to do numerous statistical tests. This concludes the SAS demonstration, Statistical Tests 1.